Hi everyone. Today we're going to be talking about quantitative changes in our equilibrium systems. Yesterday we spoke about Le Chatelier and there were no numbers involved. It was pure qualitative. Which way is that equilibrium going to shift when we put a stress on our system? Today we're going to be talking about actual numbers, and we're going to need a calculator, and let's just use a very general example to illustrate why it matters how we know, or why it matters to us, the exact numbers. So if you take a look at this system, this is the blood buffering system. You may have been familiar with it from biology class. This is the system that regulates blood pH. And if you took bio, you will know that the pH of blood has to be within a very narrow pH range. And it's pretty important for us to maintain that pH range. So, say for instance, your blood gets a little too acidic. So, for whatever reason, you are promoting the forward reaction. What doctors can do is they will administer a solution of hydrogen carbonate ions, which is a known base, okay? And what will end up happening is if I add a base, that base will react to the acidic part of the equilibrium equation and neutralize and effectively raise the pH of the blood, okay? But the whole situation here is that you also don't want to make your blood too basic. So you have to know exactly how much base you're going to put in that IV. Okay, so we know that equilibrium constant does not change with concentration, but once we change the concentration of one part of an equilibrium system, we'll disturb the equilibrium and then a new reset will happen. So we're going to start with some math, all right? And I may divvy it up into two separate videos because the math is intense, and I want to give you time to actually think about what's happening here. Okay, so let's start on the first one. So taking a look at this particular question, let's just read it out. So we've got a certain temperature, and remember, that certain temperature has to be consistent for the equilibrium constant to be maintained. Okay, and a mixture of hydrogen gas and iodine gas was prepared by placing 0.4 moles of hydrogen gas and 0.4 moles of iodine gas into a 2-liter flask. So that's important. You've always got to know what your volume is because we use it for concentration. After a point of time, we get our equilibrium. The purple color was used to monitor the reaction, and they could determine how purple the equation or the reaction went to figure out when it stopped changing, and that's when equilibrium was going on. And at that point, when we hit equilibrium, the iodine concentration drops to 0.020 moles per liter. What's the value of K? All right, so what do we know? Well, we know that the number of moles of H2, not H2O, got excited there, of H2 is 0.4 moles, okay, and my number of moles of I2 is also 0.4 moles, and we also know that my volume is 2 liters, okay. All of these are to 3 significant digits, so that's what our answer is going to be in. So for our purposes, our concentration of H2 is moles over volume. So 0.4 moles over 2.00 liters. And it's the same thing for I2. So okay. And ultimately, our concentrations, once we do this math, okay, so those are equal. So now we've got that. We're solving for K. All right. And just like usual, I like to always have my equation down, because in case you screw anything else up, at least if you write the equation for K down, you're going to get a mark for that. So here's our reaction right here, right? There's the reaction. So I know HI squared all over H2 and I2. Okay, so that's my formula. Make sure you're dealing with all gases. All of these are gases, so they're included, which is great. So now it's time for us to do our ice table. So let's do it. Now the way I always set it up is I write the equation down. So I've got hydrogen gas plus iodine gas and 2 moles of hydrogen iodide. Okay, so my initial concentration. Well, initially I have 0.200 molar of hydrogen gas. Don't forget, and do not put the number of moles in. Remember, these are concentrations. Okay, and same deal with my I2. And at this stage of the game, we haven't made anything yet. We just started. Okay, we haven't made any product. So the change, we'll use X to represent the change. And since we are consuming our reactants, it's a negative sign. And since we are producing products, it's a positive sign. And once again, don't forget that it's 2X because there's 2 moles. Okay? And at equilibrium, we will just simply go initial and the change equilibrium. So 0.200 minus X. Okay, and I'm leaving the molarity out of it because by me putting the square brackets here, it's assumed. Okay, so once again, I start with 0.2 molar minus X, and that will represent my equilibrium concentration. Same deal here. And last but not least, 0 plus 2X is equal to 2X. So now it's a matter of just simply plugging in our equilibrium concentrations. So, Kx, let's do it. So 2x squared all over, right? 0.200 minus x squared. That's the way we're going to do it. Now let's solve for x, okay? So we've got one last piece of information here. We know that the iodine concentration at equilibrium dropped to 0.020 moles per liter. So we know that this equals 0.020. So let's solve for x. So we know that 0.02 is x. Sorry about the 2 equal signs, but we'll get over it. Okay, now okay, so when I do my math, 0.2 minus 0.020 is 0.18 moles per liter. So now it's just a matter, we know what x equals. So now all I have to do is plug this x into there. All right, so let's do it. My Kx equals 2 times 0.18 all quantities squared all over and we've already solved for this, 0.2 minus x, so this is 0.18 all quantities squared, and my Kx equals 324. Okay? That's our answer right there. So that's the Kx right there. So it's just a matter of finding our equation, finding the x, and then solving for it. Okay? All right, let's try another one here. So, next scenario. How to calculate equilibrium concentrations using K. All right, so in this situation, we have a K. All right, so ethyl acetate is a solvent used in lacquers, adhesives, okay, so on and so forth. This is how we make it, okay? So acetic acid and ethanol makes my ethyl acetate and water, okay? So you may remember this. This is a dehydration synthesis, right? And we are making an ester, if you want to remember from organic chemistry. So what do we know? We know that at equilibrium, these were the concentrations of each thing. So my acetic acid is 0.210 moles per liter. My ethyl acetate is 0.910 moles per liter, and agua is 0.00850 moles per liter. Okay, so we are given, we don't need, in this situation, since we are given the equilibrium concentrations, it's not as necessary to set up an ICE table. So I'll just write that down. Since we have the equilibrium concentrations, no ICE table needed, which is kind of fun, all right? So that's good. So what do we know? We know that K is 4.10, good. Okay, let's figure out the equation for K. All right, I'm just going to scooch this up because I have a feeling I'm going to need more room. I write a lot. So scooched it up too soon. So for our purposes, CH3, CO2, C2H5, okay, H2O. Now, what I'm going to do is I'm going to make this a gas because we know that liquid water can't have a concentration, okay? So just for our purposes, that probably was a typo. Sorry about that, guys. All right, and we then also know CH3, CO2, H, and C2H5OH. Okay, you get a mark for writing that down. Now what we're going to do is actually use these concentrations and plug them in and solve for X. Okay, so when I plug it in, actually, why did I do that? Bang, bang, bang. I know what that is. It's 4.10. All right. Do I know the value for CH3CO2 C2H5? Oh, you betcha. It's 0.910. Okay. And water vapor is 0.00850. And CH3CO2H is 0.210. And we don't know what ethanol is. So that is my X. And so what I end up doing is I end up cross multiplying, right? So what ends up happening here is my X will go here and my 4.10 goes there. Okay, so X equals 0.910, 0.00850, 0.210, and 4.10. Okay, and when you do your calculations and you multiply and then divide, you will get, and once again we're going to 3 significant digits, 8.98 times 10 to the negative 3 moles per liter. Okay, this would be this is the concentration of ethanol at equilibrium, given that Kx constant of 4.10. Okay, so there's that. Let's move on to the next question. So how to calculate equilibrium concentrations using K and initial concentrations. Okay, so we have this reaction right here. So this is our equilibrium equation. The K is 4.06. It's at 500 degrees Celsius, so we know that that's specific to this reaction. If we have 0.5 moles of carbon monoxide and 0.5 moles of water, okay, so we're given these. So these are going to be our initial concentrations. We place them, actually they're not initial concentrations, they're initial moles, but then we've got the final volume, so we can figure out the initial concentrations at that temperature. So then we've got to determine the concentrations of equilibrium reactants and products. So number 1. Let's figure out, so we know that the number of moles of carbon monoxide is 0.500 moles, so 3 sig digs yet again. Number of moles of gaseous water, so once again, because it's vapor, it's in our equilibrium equation. So same deal, 0.500 moles. We know my volume is 5 liters, so my concentration of carbon monoxide is 0.5 moles per 5 liters, which is 0.100, we'll stick with the 3 sig digs, moles per liter. And same deal for the water. So, and conveniently enough, these are all the same concentration, so it makes the math easy. Don't always count on it being that easy though. All right, so we've got those concentrations, okay? And we are looking for, we also have the fact that K equals 4.06, okay? So, just because we're in that zone, let's make our archaic equation. Concentration of CO2 gas, hydrogen gas, all over carbon monoxide and gaseous water. Okay, so that'll get you a mark. And this is what you're going to plug it in. And remember, it's products over reactants. So now let's set up our ICE table. All right, so now that we've got, the way I always do it, like I said, whoops, good thing I have my eraser. CO plus water, arrow, arrow, CO2 plus H2, and both of these guys are gaseous. All right, so ice, ice, baby, let's do it. So if I have my initial concentrations, I've already determined those, right? It's 0.1 moles per liter. 0.1 moles per liter. Okay, and we haven't made any product. My change, because I'm using it, it's a negative, so negative X. And for my products, because I'm making them, positive X. So my actual equilibrium equation is 0.100 moles per liter minus X, 0.100 moles per liter, oops, minus X, I'm going into the other thing. This one, 0 plus X is X, 0 plus X is X. Okay, so now we've got to set our stuff up. So don't forget, my Kx was the concentration of CO2, H2, my products, all over my reactants. Okay, so we know the value. We know it's 4.06. We know the equilibrium concentrations from right here. Bammo. Okay, so it's X times X all over 0.100 minus X. I got rid of the moles per liter because it's assumed. 0.100 minus X. Are you noticing how beautiful this math is going to look like? So let's make life a little bit easier. Equals X squared all over 0.100 minus X, all quantities squared. All right, and the beauty of a question like this one makes you pray for one of these on a test. This is a perfect square. So you can just square the whole shebang. What you do to one side, you have to do to the other. Okay? So having said that, I now have, whoops, sorry about that. So square root of 4.06 is 2.015. And square root of X squared is X. Square root of 0.1 minus X all quantity squared is just one of these guys. Okay, now we cross multiply. So right? So when I FOIL that out, right? And then I bring all my entities to the appropriate side. So I'm gonna, and I'll have 0.2015 equals, and remember magically this turns to a positive, so X plus 2.015. So it equals 3.015, because remember 1 plus 2 You got it. I know you know this stuff. So then when I divide, my x equals 0.0668, and now we can't forget that that actually represents a concentration. So this is x. Now what we're going to do is substitute that x value back into these equilibrium things. So the concentration of CO and H2O is 0.100 minus x, right? So 0.100 minus, hold the phone, 0.0668. When I do that math, it's 0.0332 moles per liter, okay? And on my product side, it just equals x. So we already have the answer for that one. 0.0668 moles per liter. Whew, that's a lot of math. Thank God it's a perfect square, because if it wasn't a perfect square, you know quadratic formulas in your future at some point. So I know you learned a song about that in some math class. It's coming. But I'm going to take a break on this lesson. And if this is a good natural break for us to stop, and if you want to wait till Wednesday for the next half of this lesson, this is where I'm going to stop, and I'm going to pick up. Well, I'm picking up immediately. You can take a break, okay?